let's get started. So, actually, before starting class, uh, uh, I will uh, I will talk about some study time and then also study. So, actually, I read a post from Facebook. So, which means that it's regarding the study time of university students. So actually, so so we have this is a 3-unit course, so which means that so we have 3 hours. So the 3 hours per week is assigned for this course for teaching, okay, actually for lectures. Okay, but so which means that so actually I believe you are taking around 18 units per semester, which means that you are taking around 18 hours per week for classes. And then so you are I believe most of you are full-time students, which means so actually full-time workers work 40 hours per week. So and then you are taking around 15 or 18 hours for classes. So which means you need to invest the additional times actually around 18 hours, so double so actually the same amount of time of the classes for your study. So I hope actually so this is also a 3-unit course. So which means so you are investing 3 hours for classes actually for lectures. So which means you need also invest your additional 3 hours for studying this course, right? So actually the first homework and then first lab assignment were posted on the Blackboard. And then sorry, the lab assignment was posted this week. And then I said that if you are not familiar with this design or system verilog, then please start early. Okay, so you can get help from TA or me. Okay, so if you struggle writing verilog codes, or if you struggle installing some tools such as verilog, then please stop by TA's office, or also you can stop by my office at the appointment. Okay. If you feel difficult in this course, please ask questions or post questions on Piazza. Also, you can stop by. You can get help from me or TA's. Okay. Also, I hope you can invest a minimum 3 hours per week for this course. Okay. Okay. So, in the previous class, we covered we learned about the instructions and architecture. So we learned about the RISC-V instructions and architecture. So I said that instructions and architecture is a collection of instructions. Okay, so actually, so I explain about the processor model. So processor receives instructions, and then processor generates result of instruction. But these results of instructions are defined in instruction set architecture. Okay, so I said that actually I already the instruction and manual of the RISC-V on Piazza. So actually the number of pages is around 100 pages, right? So but if you are interested, you can read the instruction manual. So which means that the result of the instructions and then how the instructions are organized are actually defined in the instructions and manual. Okay, and then based on this manual, the like instructions and architecture, hardware engineers or computer architects design a processor that support corresponding instructions and architecture. So which means that if a processor supports RISC-V instruction, then we need to design a processor based on the instruction manual of RISC-V instruction set architecture. Okay, and then which means that if our defined instructions are given to a processor, then a processor needs to generate the promised result. Okay, the defined result. And then I said that actually when an instruction is executed in a processor, then these instructions change states of a processor, and then which means actually instructions change data in register file or main memory. Okay, and this is very important. So actually in chapter 2, we learn about the instructions and architecture of RISC-V. And so which means that actually the today's class I will teach about the basic instructions such as the arithmetic instructions or memory instructions. And then when I explain about these instruction types, then I will explain how the processor, how the state of processors are changed by certain instructions. Okay. Okay. So I also explain about the RISC-V instruction. Also, you can find this RISC-V reference card. Actually, you can find this green card. It's called the green card in the first page of the textbook. Okay. So actually, this reference card, this is the basic instructions of RISC-V. So actually, I also make some table that is the basic instructions of RISC-V. Actually, it's not small. So as you can see, you can find that this is the base integer instruction IB32I. Okay. So as I explained, the RISC-V instructions are based on the integer instruction like IB32I or IB64I, and then we can add more instructions as extensions on this baseline instruction. Okay, so which means that if we add m extensions, then we can add multiply or divide instructions. It's an example. Actually, so if you read the Excel file, so I will go to I instructions of Excel. It's an Excel file posted on the PRJam. Then you can find this table. Okay. So if you read this table, if you see this table, then you can find the category of instructions like the load, store, keep. So you also learn about these types of instructions, and then also you can find the instruction name here. So like the add, I, and sub, like here. Also, you can find the instruction form. Okay. So when an add instruction is given to a processor, this add instruction has the form like this. This is RD, RS1, RS2. So I will also explain about the meaning of this RD, RS1, and RS2. Also, you can find the instruction format, the instruction name, and the meaning of the instruction. Okay, in variable. So actually, if you see this table, then you can also recognize some the meaning of RISC-V instruction, and then also the format of instructions. Okay, okay. Actually, it's very similar to this RISC-V reference card, but I also added the more information on this table. Okay, so let's think about the basic instruction, basic RISC-V instruction. The first type of RISC-V instruction is the arithmetic operation, which is called the arithmetic instructions. So what does that mean? Arithmetic means that it's somewhat mathematical arithmetic, such as the addition, subtraction, multiplication, or division. So the very basic arithmetic operations. Okay, but as I said, RISC-V, the baseline RISC-V instruction supports only add and solve instruction. Okay. Okay, actually, in order to support the multiply or divide instructions, then we need to add the and extensions. Okay, so this is the example of the arithmetic operation, like the add instruction. So add A, B, C. So this is the basic format of arithmetic instruction. So, and then what is the meaning of this instruction? So actually, if we see the name of one instruction, so this is the add, so we can figure out, oh, this instruction performs addition, right? And then this instruction has 3 operands. Okay, so which means that it's a data required by instruction, and then the meaning of an instruction is the A equal P plus C. Okay, so in the same way, so let us say we have the solve instruction. It means the subtraction, and then solve instruction has also the same form, like the A, B, C. So what does that mean? A equal B minus C. Okay. So, and then actually, if you see this table, so actually there are 5 instructions in RISC-V 32i for arithmetic instructions. As you can see, the add instruction here and solve instruction here. But we will also learn about the add I. So add I requires the immediate value, but I will explain later. So, but if you see that these arithmetic instructions, then you can find that the form of instruction like add, RD, RS1, RS2, so actually it's A, B, C, and I explain about the operand of the add instruction. Also, you can find solve has the same form. So, which means actually the instructions and the RISC-V instruction set architecture is the RISC type instruction. So, which means that it's simple because it's simpler than CISC type instruction. But and then the advantage of RISC type instruction is that the instructions have the similar forms. Okay, so for example, add and solve, it's the same type of instructions as arithmetic instruction. These instructions have the same format, but same rules for the instruction. Okay, so why? Regularity. So when we design an instruction for a processor, then we also need to consider the regularity of instruction forms. Okay. So for example, we can define some different instructions like add, for, A, B, C, D. So if we define the different form of instructions like add for A, comma B, comma C, comma D, then we can define like the A for B plus C plus D. So then if we see that this instruction, so actually in a RISC-V, this type of instruction does not exist. But if the instruction have the different form, then actually this instruction. When the instruction is given to a processor, then processor needs to decode, which means that the processor needs to divide the instructions and then needs to figure out, oh, what is the name of the instruction and what are the operands of the given instruction. But if the instruction have the different forms, then we need to design complex decoder, complex hardware decoder. So then complex hardware means that we need to design a complex hardware, so which means we need to invest more hardware resources. And then another problem is that if the hardware is complex, then this hardware require longer clock cycle. Okay, so which means that the frequency becomes, so we need to use the low frequency, low clock frequency, okay, because the hardware is complex. And then we know that we actually T, when we consider the performance of a processor, P is the instruction count, CPI, and clock cycle time. So this is also very important for the performance of a processor. And then if a processor becomes very complex and we cannot use fast clock, then performance can be degraded. That's why we actually the hardware engineers who are computer architecture favors simple architecture, right? Simple hardware. And then simple hardware can be designed from regular instruction forms. That's why the instructions have the regular forms. Like A has the 3 operands and then A4. So A stores the result of operations, and then we use the B and C as the operands of the add instruction, the source operands. And then another instruction, solve, which is solve, has the same format, A, B, C. So this is so we can figure out that this is the destination. Then these are the sources. Okay, so they have the same form. So actually, if we see the other instruction like logical instruction, so you can find that these instructions have the same format. A, B, C, so or A, B, C. Okay. So you mean this one? Yeah. So that's a very good question. So actually, I will explain. So if you see that this RISC-V format, so you can find that this format information on the RISC-V green card. So actually, this RISC-V has the several formats like the R-type format, I-type format, S-type format, blah blah blah. So format means that actually when we learned about how the programs are translated, actually high-level program codes are translated into assembly languages. The assembly language means that is instructions and then operands of the instruction. So we can design assembly code with the RISC-V instruction, but this assembly code also uses the English characters, right? Like add, R1, A, B, C. So these are English letters. And this is not to actually the processor is the system, and then I said that is the system can only understand binary code, electric signals. Okay, actually. So this assembly code need to be translated into the machine code, like 100100100 blah 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 blah. The format means that actually this assembly instruction is translated into the binary code, which have the 32 bits, and then format means that how the instructions are translated into the machine code. So for example, this is the R type instruction. And then if you see the add instruction here, I add A, B, C, but as you can see in the table, you cannot find any A, B, C here. So actually, A is the RD, B is the RS1, C is the RS2. And then in order to represent this RD, RS1, RS2 or add instruction, we need encoding rule. So which means that this instruction is translated into the machine code. And then when this translation is when the assembly instruction is translated, we generate the machine instruction based on this encoding rule. Okay, so encoding rule, if I'm actually there are several formats like here. So add is the R format, and then so RD is represented here, RS1 is represented here, RS2 is represented here. And then in order to represent the add instruction, we need to use this field. Okay. So R format means that. So as you can see, so add solve is the also same format. So which means that either this formatting rule, add instruction can be translated into this machine code. Also the solve instruction is the R format instruction. This instruction can be also translated into the machine code using this formatting rule. Okay. So actually I will explain about this format later. So yeah.
두 번째랑 세 번째 소스가 같은 것처럼 보이는데 A, B, C라고 했을 때 B랑 C가 차이가 없어 보이는데 순서가 바뀌면 사조에 굉장히 달라요.
So very good question. But so let me use the add instruction like plus, then you don't need to consider about the order of operands, right? But if we need to use the solve, then we need to consider the order of operands. Okay. So actually, so even though we change the order of the source operand like C and B, but C plus B is equivalent to the B plus C. It's not a problem, but when you consider about the solve instruction, it's the same format. But if we change the order of source operands, the result will be different. Okay. So actually, instruction is encoded into which means that translated into the machine code, and we need to keep the rule. So this encoding rule. So which means that B should be here always. The C should be represented by this field. Okay, so we need to keep the encoding rule. But it's not a problem for only add instruction, but for other instruction, it can be it can generate the different result. Okay. Okay. So Okay, so let's see the example code of the how the high-level language code is translated the assembly instruction. So this is a very simple C code, G plus H, and then I plus minus and I plus J. Then how can we translate this C code into the RISC-V assembly code? So we just learn about the add instruction and then sub instruction, and then it's very simple. So in order to perform this operation with the G plus H, then we can use the add instruction. So first we add G and H, and then store the result of G plus H into some temporary place like P0 for the temporary variable. Also, we can perform the I plus J, and then we can also store this result into the temporary space like P1. And then not perform subtraction, then we can perform the P0 minus P1. So we require sub instruction. As you can see, the result of sub instruction is stored in the app. So this is the typical C code, and then as you know, so we can use any variables for C code. And then these variables can be here. So we can also map these variables in the assembly instruction. But really, it's not true. Actually, we need to translate these variables into the operands, real operands of an instruction. So I said real operands. So you may not understand why we need to use the real operands. So think like this. So actually, when a variable is declared in a high-level language like int G, and then where is the data of this G, variable G? In the memory, okay? All data and then all data, including actually instruction. So all data are stored in memory of a computer system. So which means if we declare a variable with a high-level language, and then which means that we just assign a memory space for this variable in a computer system, and then the data of this variable is stored in the memory. Okay, but actually, computer processor does not access the data in the main memory directly. So actually in chapter 5, we will learn about the memory hierarchy. But if you see just think like this. So if you see the processor, and then actually the system of the computer system, which is composed of processor and memory. Actually, you can find that the processor and memory are separated, which means that the processor is implemented in a single chip, but the main memory, like DRAM, is the out of this processor chip. Okay, so actually, it means that if the data is moved from the main memory, it will take very long time. Okay, so we can say, we can feel that it's very fast, but for the processor, it's very slow. Okay, because the clock frequency is very fast. So actually, and this arithmetic instruction is executed. These instructions with data from very fast memory because main memory is very slow. So these instructions read data like required operands from very fast memory. And then actually the size of this fast memory is also very small. Okay, and then this fast memory is called the register. It's called register. Okay. So let's learn about the register operand. Okay. So as I mentioned, when the add instruction like f equal g plus h, I like rewrite. So f equal g plus h. Now highlight the language. So actually, when this variable is declared, this variable is located in main memory. Okay, so which means therefore G is here, and then H is here. So yeah, and I explained that the main memory is very slow compared to processor. Okay, so think about the size of the main memory. So what is the typical size of the main memory exactly? It's around 4 GB or 8 GB, right? So like 4 GB or 8 GB. Actually, it's very large. But in a computer system, if the hardware is large, so it means the memory size is large, which means this memory is slow. So when an add instruction like this add arithmetic instruction is executed in a processor like F, G, H. So if this add instruction directly receives data from main memory, it will take a very long time. Okay, so you don't like this situation. So instead of this, computer processor has the very small. It's very small compared to the main memory. The size is very small, but this memory is very fast. So for example, when we access this data from the main memory, then it will take 300 or even 1,100 cycles. So which means like in order to perform the add instruction, like add F, G, H, then if the data is directly accessed from the main memory, then the CPI for this instruction can be about the 300 or 1,000. Okay, right? But we don't like this situation because of performance. Okay, if the CPI is 300, or if the CPI is 1,000, or it's ridiculous. You cannot use fast computer. So instead of this data is temporarily stored in the smaller, very small, actually, and then faster storage space in a processor, inside of a processor. Okay. And then this add instruction access data from this smaller and faster storage space. Then, as I said, this space is called the register. This memory space is called registers. Okay. And then actually this arithmetic instruction access the data in registers. Okay. So as I mentioned, arithmetic instructions use register operand, which means that, so as I mentioned, so it's add, A, comma, B, comma, C, but this add instruction reads data from B and C, and then actually B and C is the registers. Okay. The RISC-V has the 32 entries, 32 register entries. Then the width of the a single entry is the 32 bit. So what does that mean? Actually, I said that register size is very small. So, and then each register has the register numbers, and then we have 32 registers. So we can say that in a RISC-V has the very fast storage space called the register, but number of registers is 32. Okay, so which means we can use the register from X0 to X31. So this is the register number. And then the size of a single register, it's called the width. Okay, the size of a single register is the 32 bit. Okay, so as I mentioned, the A, B, C, actually the computer can only understand the binary numbers. So these numbers are stored in this register. Okay, the size of the register is the 32 bit. So which means the size of actually the maximum size of this data is defined by size of a single register. Okay. So for example, it's a 32 bit. So it's a 32 bit register. So which means that if this is the unsigned integer, then we can have the number 0 to 32 minus 1. Okay, this is the maximum number of the P. Understand? So this is the hardware. So the hardware is the real component. So we cannot use the unlimited hardware in the processor. So which means the size of the hardware is the limited. Then so we also use the limited number of data. Okay. RISC-V support the 32 registers, and then this group of registers are called register file. Okay, so there are 32 registers from X0 to X31, and then these registers are managed in a single memory component, and then this memory component is called a register file. Okay. It works. And then actually the size of a single register defines the size of a processor, which means that sometimes we can call our processor is the 64-bit processor. So what does that mean? Which means actually a size of a single register is the 64-bit. So which means a single instruction can handle 64-bit data. So which means our computer is the 64-bit computer. So actually in this course, we are learning about the RISC-V 32i, the IB32i. So actually this number defines the size of a single register, which means we are learning about the 32-bit computer system. Okay, you understand? So this number is the width, so size of a single register, and then this 32-bit data is called word. So just delete this. It's a word, and then also we can also think about the 64-bit computer system, and then most of the computer system is the 64-bit presently, and then 64-bit data is called double word. Also, RISC-V supports the 64-bit 64-bit register, and then its instruction is called the IRISC-64I. Okay, I said this number is the size of a single register. But in this course, we will learn about the 32-bit RISC-V, so which means the size of the RISC-V is the 32-bit. Also, we can also find the design principle. Smaller is faster. So why do we use registers? Because the size of the register is much smaller than the main memory, which means the register is very fast, right? So, and then when an instruction like add A, B, C, access these operands, then if we read this data from registers, then it will be very fast. Okay, that's why we use registers. So this slide shows the registers in our processor. So as I said, RISC-V has the 32 registers from X0 to X31, and then the size of a single register is defined by instruction set architecture. So we are learning IRISC-V, so which means the width of register is the 32. It's a 32-bit length for the IRISC-35 and 64-bit length for IRISC-64I. And from 32 registers, X0 is the special register, which means X0 has always 0. So what does that mean? Even though we add some values to the X0, like add X0, X1, X2, and then let us assume that X1 has 1, X2 has 2. So we perform the 1 plus 2, and then by definition of the add instruction, the result 3 is stored in the X0. But I said X0 is a special register, and the X0 has always 0 value. So which means, in this case, even though 3 is stored in the X0, then when another instruction reads data from X0 has 0. So always 0, even though some values are written to X0, but X0 just to return 0 always. Okay, this is a special register. Okay. So 0.
다음 클락스에
무조건 0이 되는 그냥 업데이트 안 돼요. It is not updated, but the value of X0 is always 0. Okay, it's not updated. It's a special register. Also, the processor has the special register called program counter. But we will learn about the program counter later. But just remember that program counter is also a special register, and then it's also very fast. So I also copied the definition of a register from Wikipedia. So you can read the definition of the register here. So it's a quickly accessible, then also small amount of storage. Okay. So actually, in a previous slide, I introduced them. So in the arithmetic instruction, like add, so when F equal G plus H is performed by a processor, And then I express the instruction for this F equal G plus H as the F G H. But we learned that RISC-V arithmetic instructions use register operands instead of the memory operand. So actually, this instruction needs to be rewritten as the instruction name is the same, but x1, x2, x3 like this. So in RISC-V instruction, x represent each register, and then this number represents the register number. So if you see that this register 5, you can find that x0 here. So you can find register numbers. Okay. So what does that mean? Add x1, x2, x3. So which means this add instruction reads data from x2 and then reads data from x3 and then performs addition plus instruction, then store the result to the x1. That is the meaning of this add instruction. So just remember that the add arithmetic instruction use register operand. So when the register operands are used by an instruction, then we need to specify register numbers. So if you see the this keyboard, then you can find that so the format of the add instruction is the RD, RS1, RS2. So actually, if you see in the operand of the add instruction, R means the register, okay, and then S means source. So which means that RS1 is the source register 1, RS2 is the source register 2, and then RD is the destination register. So meaning of this add instruction is the like this. So as you can see, this is the RD. So it's the destination register number. Then RS1 is here, RS2 is here. R means register. Okay. So we can understand the assembly instruction of RISC-V like this. You understand? Okay. So actually this is the RISC-V register. So actually this X0 is the special register, and then we can use other registers as the general purpose register. So which means that we can use the other registers with some purpose of the application or purpose of an instruction. But that's just recommendation. So actually this recommendation is to provide the compiler. Actually, compiler assigns the data to a specific registers. But we learn about this special specific register, which means the purpose of register later. So as I mentioned, this C code should be translated using register numbers, not the real variable name. So actually, this C code is translated, then we need to use this add instruction or sub instruction need to access register. Okay, these arithmetic instructions cannot access data in main memory. Arithmetic instruction can just access data in register file. So which means we need to use the register numbers like this. So let us assume that G is in the X20, the register number 20, and the H is in the X21. So it performs the G plus H, and then we store the result of G plus H into the temporary register. So it's the X5. So we need to write assembly code like this. Okay? So just remember, arithmetic instruction require register operands. So which means we need to define the source register numbers and destination register number for these instructions, this type of instructions.
네.
예.
레지스터 수많은 인스트럭션으로 지나갈 때마다 레지스터가 계속 값이 바뀔 텐데
맞죠?
바뀌는 게 위에서부터 순서대로 바뀌는 건 따로 알고리즘이
그냥 위에서부터 순서대로 바뀌는 거죠. So here's that how can register how can register be updated? So it's the same. Actually, when we write a code, so we assume that the statement. So actually, the instructions of code is executed from top to bottom, right? So like A equal 1, A equal 2, A equal 3. Then what is the final value of A? A is 3, right? That's how we understand the code. And it's the same to the assembly code, okay, right? The instruction in assembly code is executed from top to bottom. So which means like add x1, x2, x3, and then the next instruction is to add x1, x5, and then x4. The final value of x1 is the x1 equal x5 plus x4, right? So instructions are executed from top to bottom. Okay. And then let's learn about the memory operation. So why do we use memory operation? So when I explain about the registers, so I said the register is the very small memory, but we have main memory. So which means the computer system. A computer system has main memory, and then main memory size is very large, around the. So recently we use 4 GB or 8 GB of main memory. And then also I explained that when a variable is declared, the space for this variable is assigned in a main memory, actually. So like for int G, and then G is assigned in main memory. But I explained that arithmetic instructions access register file only. So I frequently use RF for the register file, like add x5, x20, x21 here. So this add instruction just access the register file. It's ridiculous, right? G is here, but add instruction access the only register file, which means we need to transfer the data in main memory into register file. Right? This type of instruction is required. You understand? Data is in main memory, but actually other instructions, so normal RISC file instructions just access register file only. And how can you access this data in the main memory? The data in main memory needs to be transferred to the register file. And then we also require this type of instruction. Okay. So which means that we need to transfer data from main memory to register file. Also, we also need to transfer data from register file to the main memory. This type of instruction is called memory instructions, like load and store. load and store. So actually, so when a G is declared, then G is assigned in the main memory, and then we can also store some data to G here in the main memory. And then in order to perform the G plus H, then we need to transfer this data to the register 5. Then how can we perform this instruction? So G is here, and then H is here. And then, in order to perform the G plus H, we execute the add x5, x20, x21, which means x20 needs to have the value of G. So we need to use load instruction, such as the first load. So this is the load instruction. It means the load word. Load, and then this is the destination of load instruction, like x20. And then we need to read the data from the main memory. So how can you read the data from main memory? We need to use on address. Okay, like the address of G. So this means the address, the and sign represent address of a variable. So actually we need to access the content, the data in main memory using an address of the target data. So why do we need to use address? It's simple, actually. So think like the apartment, like it is called condos in American, so actually in Korea, so we frequently use apartment. But so how can we find the home, a certain specific home, specific house for apartment or condos? Actually, the apartment has the same houses. Many houses. We can find many houses in the apartment building, and then how can you find the specific house? We can find specific house using house number, right? Like so, house number 201. So this is this house, right? It's sent to memory. So actually, the main memory. Main memory is very large, and then each space of the main memory is pointed by some number, and then this number is called address. Okay, so we can access a certain space of a main memory using address number. So, G is here, and then we need to also, in order to access G in main memory, then we need to use address of G to transfer data G from main memory. Okay. Then so this type of instruction is called memory instruction. Okay, and then the data in main memory is accessed, and then this data is called memory operand. You understand? Okay. So this is the example. So this is the decoded intelligence actually. So that's why. So actually, this is if you see that this code, you can find that. So I declare the variable A. So then as I mentioned, when a variable is declared, you can see, and this variable is assigned in the main memory, like A. And then in order to access the data in main memory, I mentioned that we need to know the address the address of this variable in main memory. Okay, and then I may also mention that when I represent an address of data, certain data, I use AND operator. Okay, so which means the address of a variable A is using the AND operator. So you can find this printf statement of C, also another printf statement here. So this printf is the A equal, then the data of A, print the data of A. Then what is the result of this printf? It's 0, right? It's very simple because the A has the value 0. And what is the output of this printf? This is the address of A. So this is not 0 because this is the address. So we don't know the actual address of this A because the address of A is determined by operating system. So we can see that some numbers, very large numbers, that is assigned to this address of A, like 0x001, 8, 7, blah, blah, blah. So very large number. So this is the address of A. So just remember that when I use this AND operator before a variable A, so which means this is the address of A. Okay, just remember. So this is another example. Also, when a data is stored in address, that we can consider two different storage formats. So it's the first format is called the reader endian, and then another format is called the bit endian. Why? So actually, when an address is assigned to a data, we assign address 1 for byte data. So what does that mean? What is a byte? What is a byte? Byte means 8-bit data. So 1 byte means 8 bits. It is so which means if we mention 1 byte of data, which means this data includes 8 bits. What is a bit? Bit means the 0 or 1, some digit of the binary number. Okay. So actually, in a computer system, the most of computer systems use byte address, which means we assign address 1 for each byte. So which means, so this is the main memory. So this is the 1 byte, which means the 8-bit of data. So the address of first byte is the 0. Is a 0. Okay. And then the address of the second byte is the 1. This is also 8-bit. And then the next byte is the address of next byte is the 2. That is the byte address. Then, but usually when we declare integer data, like int A, the size of integer data is usually 4 bytes. It's a 32-bit. So that's why we can the size of actually the range of integer data is the -2 to 31 to 31 minus 1. Okay, so integer data has the range. Okay, because this is the size of the integer data is the 4 byte. Then actually when we handle the 4 byte of data, we need to use the load word because the word means the 4 byte of data. So, but we need to decide how is 4 byte of data, the stored to be integer, is stored in a memory, because the memory address is the byte address. So actually, this is the byte data. Then, in the load word, we need to access the this memory space, but the size of the data is the 4 byte. Then we need to decide how this data is assigned in the memory. So there are two different methods. So for the little endian and then big endian. So little endian means that lower part of data. So this is the if we represent this number using the bit data, like so we can represent this data using the bit number 31 to 0, right? And then actually this 0 is called the RISC-V, least significant bit. Okay. And then when we use the little endian method, then the lower part of the bit number, so which means that the bit number is smaller, the lower part of data is stored in the smaller address of memory. So which means in this figure we can find that. So this is the this is the bit number 7 to 0 for this data. It's a byte data, right? So bit number 7 to 0. This data is assigned to memory address A. And then the next byte is bit number 15 to A is assigned to the A plus 1. A plus 1. And then the next byte is assigned to the A plus 2. This is the little endian memory format. And big endian is so it's actually the large, the upper part, the large part of the bit number, like 31 to 24, is assigned to the lower address part, like A. So it's an inversion of the little endian. Okay, but RISC-V use the little endian memory system. Okay. So just remember how the little endian and the big endian is different. So in a big endian, the upper part of the data is stored in the lower address, but in the little endian, the lower part of the data is stored in the lower address. Okay, so then RISC-V is the little endian format, little endian memory system. Okay. So this is the example of memory instruction. And then this is the C code. And then as you can see, so this C code accesses the array data, the array data A, and then read data from A8, so the 8th element, the index number 8 of array A, and then performs the H plus A8, and then store the data to the 812. Okay. So first, so this is the array. When the array data is declared in a C, then the base address. If the first element of array is the A0, then A0 is assigned to this main memory. And then the next address, A1 is assigned. And for the next address, A2 is assigned. And then let us assume that the size of this single element of array A is the 4 byte. It's the word. So if the address of A0 is the address small lowercase a, then what is the address of A1? So size of element is 4. So this is the, so we use the byte address, and the size of a single element is 4 bytes. Then what is the address of A1? That's why A plus 4. This is the A plus A. So which means if we know the base address of an array, like A0, address of A0, and then if we use the index number of a target element, then we can calculate the address of a certain element in an array, like this. A3 is the A plus 3. Then how can you access the AA in the main memory? So let us assume that the base address of array A is stored in the register X22. Then how can you calculate the address of AA? It's X22 plus 32, right? Because the size of a single element is 4 bytes, and then this is the 8th element. So this is, so 32 is the actually 4 multiplied by 8. So this means address of this target of load word. And then this is the address. So load word performs the X22 plus 32. So calculate the address of A8. And then using this address, read the data from the main memory, and then this data is stored in the destination register X9. So which means X22, sorry, X22 as the address of base address of array A. So this which is equivalent to the 0th element of array A. And then in order to access the A8, so we need to know the address of A8. So address of A8 is equal X22 plus 32. So this means the X22 plus 32. So this is the called the offset. The offset is added to the data in X22. And then using this address, then X22 plus 32 is A8. Then the data is read from main memory here. Then this data is stored in the register file X9. This is the definition of a load instruction. Okay, so this is the address part, and then with the address, the data is read from main memory, and then the data is stored in the destination register X9. And then let us assume that H is already in the X21, right? So we can perform the X21 plus X9 using the add instruction. And then this result is also stored in the X9. So X9 currently has the H plus AA, right? So firstly, when a load instruction is executed, it's a very good example of this case. And the first load instruction is executed, X9 has the only X9 equal A. And then when this after add instruction is executed, X9 has the H plus AA. Okay, right? Then this is the store word. Store instruction is the inverse of a load instruction, which means that read data from register file, and then this data is transferred to the main memory. So actually, when this in code is executed, then we need to store the result of H plus AA into A12. Address of A12 can be also calculated using the same way. This is the base address, and then this is the offset. So offset is the 12 multiplied by 4, because the size of a single element is 4. And this is the 12th element. I said the direction of the store instruction is different. So the definition of the store instruction means that read data from X9, because X9 now has the H plus AA. Read the data from X9, and then this is the target address. The data over X9 is stored in the target address. This is the X22 plus 48. It's the A12. So read the data from X9 and then store the data to the main memory using this address. This is the definition of two instruction. Okay. So this time I explain about the very simple arithmetic instruction, but you need to remember that arithmetic instructions of this fine just act as register file. So because register files are very small and fast. So we need to transfer data from memories between memory and register file, right? Because the data is actually all data exists in main memory. So for transferring data from main memory to register file or from register file to main memory, then we need to use memory instruction like load instruction or store instruction. Okay, so this is a very important concept of the RISC instruction. So please remember the operand, the register operand, and the memory instructions in the RISC file. Okay, it's a little bit late. Sorry about that. Any questions? Okay, thank you for your attention. See you next time. 감사합니다.